I'm greeting you and the listener from internet and the audience from the Baku State University. And this work was done actually by Dr. Rasmiyya Gasimova, and who is from our collaboration. But today she is not able to participate here, and she requested me to give talk on behalf of her. But I try to answer your question at the end if I am able to answer your questions. Therefore, my mission is to give this talk and on behalf of Professor Dr. Rasmiyya Gasimova. With your permission. Okay. But the topic of today's of this talk, and back slide, okay, please, back slide, okay. As you noted that the first slide, the first one, okay, yeah, okay, yes. This is the annihilation, okay, annihilation, neutrino, anti-neutrino, no. Muon neutrinos and electron anti-neutrinos, and at the same time, Tauon neutrinos, we mean. Muon neutrinos or Tauon neutrinos and electron anti-neutrinos into muons, Tauons, and positrons. And the case of transverse polarization. Okay, and in this topic, and it is investigated the transverse polarization case, that we mean that the produced muons, Tauons, or positrons are transversely polarized. Okay, and here we investigate. Here the author investigate the annihilation of different flavor of neutrinos and anti-neutrinos. And this process is proceed via the W boson, via the charge neutral current, charge weak currents. Next slide, please. Okay, and recently Pamela and AMS-02 experiments has registered the positron abundance, positron excess in the cosmic rays. Okay, and the energy of the positrons and is registered between 20 GeV and 300 GeV. And the behavior of positron spectra and electron spectra beginning from the 20s GeV, around 2030, and behaves themselves differently for electrons and for positrons. And the question is that, and where is this abundant excess of positrons? And this was registered, the positron excess was registered by Pamela and, as we indicated, AMS-02 experiment. Next slide, please. Next slide. Nobody. Next. Okay. Before it, okay, and the indicated reaction here is one of the possible sources of cosmic charged leptons. And here on the right side of the reaction, we mean under the letter L, muon and tauon with the negative sign, and nu L means that the muon neutrino and tau neutrino. This is one of the possible sources of cosmic charged leptons, muons, tauons, and positrons of high energy, or maybe super high energies. And therefore, this reaction is very or has importance for investigation. Next one, please. Okay, next one. And these processes here, two processes are investigated, and in the results of the muon neutrino and electron annihilation, muons and positrons are produced, and in the second reactions, and tau lepton and positrons are produced in the annihilation of tau neutrino and electron antineutrinos. All these processes have been proceed in strongly magnetized, hot magnetized medium and stellar medium. Next one, please. Okay. And the purpose of this work is to investigate the indicated reaction, annihilation reaction, when the initial neutrinos and antineutrinos moves on the plane or XY, and perpendicular to the z-axis, which is assumed to be directed along the z-axis. The direction of magnetic field and the z-axis coincide here. And here it is the aim is to determine the low Landau levels on which the muons and positrons can be produced, to determine the Landau levels where muons and positrons or tau leptons and positrons can be produced. Next one, please. Okay, and the cross-section of this reaction is determined by this expression, and here the Fermi-Dirac distribution function of final charged leptons and positrons have been taken into account, and here T5, where is the indicator, please? Okay, T5 is the coefficient which contains spins of the particles, final charged leptons, and this letter I squared is the Laguerre functions, And here G Fermi constant, H magnetic field strength, and this is the parameter characterizes magnetic field. H0L is a parameter, is the magnetic field strength is approximately 10 in power 19 Gauss. Next one, please. Okay, and also in the previous reaction, EI primed is energy of positrons, and primed belongs to muons, and PZ, Z component of the momentum of muons, and PZ prime, momentum of positrons. Sorry, PZ belongs to positrons, PZ prime belongs to muons or tauons. And FL minus is Fermi-Dirac distribution function of charged leptons. F electron plus belongs to positrons. It's the Fermi-Dirac function of positron gas. Next one, please. Next slide, please. And differential cross-section of the process contains the Laguerre function, and whose argument is x, which is determined by this expression. And here theta is azimuthal angle of the momentum of initial neutrinos, prime theta prime initial antineutrinos, polar angle of the momentum of initial antineutrinos. Also alpha prime are the azimuthal angle of initial neutrino momentum, alpha prime the azimuthal angle of the initial antineutrino momentum. Omega is the energy of muon neutrino or tau neutrino. Omega prime is the energy of electron antineutrino. Next slide, please. And we have noted that T5 is the spin, is the coefficient which contains the spins of the particles. Here, zeta is the spin, the projection of the spin of positrons. Zeta prime is the projection of the spin of muons or tau leptons. And nu primed are parameters, and beta primed also are parameters. And E primed are the energies of charged leptons in a magnetic field. And a magnetic field is assumed to be homogeneous and constant. Next one, please. Okay, and also zeta and zeta primed. Okay, we indicate zeta is a projection of the spin of positron. Zeta has this has the value +1 or -1. And since we consider the transverse polarization in this case, it means that when zeta is plus, it means that spin is oriented along the magnetic field. It means that it is perpendicular to the momentum, positron momentum. And when zeta is minus, it means that the spin of positron is directed against or opposite to the magnetic field direction. At the same time, it is perpendicular to the momentum of electron. Zeta primed belongs to muons or tauons, and we indicate it is derived that the function the Laguerre function, and when x is 0, distinguished from 0 when delta n, it is the difference of Landau, the principal quantum number n and n prime. N is the quantum number which describe the energy level, Landau energy levels. And n prime is the Landau quantum number, or the principal quantum number which describes Landau level for muons or tau leptons. Then delta n, the difference, this principal quantum is plus. In that case, Laguerre function is not 0. Only delta n is plus 1. If it is minus 1, the Laguerre function is 0 and the processes stop. Next slide, please. Okay, and when delta n is plus 1, in that case, the reaction has such cross-section. Okay, next slide, please. But we have, it was derived that but only muons, positrons and muons, or positrons or tau leptons are produced in that case when positrons are produced on the first Landau level, muons produced on the 0 Landau level, or when positrons are produced in the second Landau level, muons or tauons are produced on the first Landau level. But if you can see from here that the number n for positron is 1 unit more than the quantum number n prime. Okay, and but next one, please. And here we see that. Next slide, please. We see that positrons are produced on the, or can only be produced on the first Landau level, second Landau level, third Landau level. But muons can be produced on the ground Landau level, first Landau level, second Landau level. From here we see that positrons cannot be produced on the 0 Landau level, on the ground Landau level. Ground Landau level. When muons are produced on the ground Landau level, positrons are produced on the first Landau level. Next one, please. It means that the production of muons or tauons on the ground Landau level is impossible, is prohibited, is allowed. But the lowest level where muons or tau leptons can be produced is the first Landau level. The first, okay, the lowest Landau level where muons or charged leptons can be produced is the ground Landau level. But for the positrons, the lowest level is the first Landau level. Next one, please. What does it mean? For muons, n prime is 0 when muons or tau leptons are on the ground Landau level. These quantum numbers are satisfied. It means that when muons are produced on the ground Landau level, their energy is equal to their rest mass. Now let's suppose that if muons, in the final state we have muon and positrons, or tau lepton and positrons. Muons are produced on the ground Landau level. It means that their energy is equal to their rest mass. They do not have additional energy or additional kinetic energy. They are not able to move in the medium. But positrons are produced, next slide please. Positrons are produced on the first Landau level. On the first Landau level. It is derived from the third component of the momentum. This is PZ component, okay? What we have received in the result? In the result we have received that the produced positrons have the 0 energy or the minimal energy. They are not able to move and they stay in the medium, but the produced positrons have high energy relativistics. They leave the medium. They leave medium and they are they contribute to the cosmic rays. But muons and tau leptons, lives in the magnetized medium. So it turns out that we have contribution to the cosmic rays at the expense of positrons, but not at the expense of muons, because muons stays there, muons stay there, not live. Muons are not able to leave the magnetized medium. Next one, please. But the muons, which are produced at the expense of these reactions, are emitted to the cosmos, okay, to the space, and they contribute to the cosmic rays, cosmic high energy particles. But positrons, other particles, charged leptons, muons, tauons, stay there. Okay. Next one, please. Next slide, please. And we've indicated that the energies, the characteristic energy for positrons is between 20 GeV and 200 GeV, which are met in the cosmic rays. And but such energies, then positrons with this energy can be only magnetic fields in the magnetic field with this strength. Okay, we have calculated. We have found that the intensity that the sources, the magnetized sources with this intensity, with this strength, can only produce the positrons of such energy, okay? Because initial neutrinos have such energy, give energies, okay? But in any case, then electrons, electrons should gain such energy. Electrons only should gain such energy in a magnetic field with this strength. But it means that the magnetized object, astrophysical or cosmic objects, should exist in the space. But these objects, magnetized object with this magnetic strength, can emit positrons of this energy. Next one, please. So the conclusion. So they observed positron excess or abundance, or one of the sources positron excess observed by Pamela and AMS-02 experiment. One of the sources can be the investigated reaction, the annihilation of different types of neutrino into charged leptons, muons and positrons, or tauons or positrons. And the sources of this object should have such magnetic field. The magnetic field should contain such field strength, 10 in power 22 Gauss or 24 Gauss. Okay. Thank you for your attention. Any questions, please?
Thank you very much, Dr. Hüseynov. Next. Have a question, please.
Hello. I have one question. I would say, you say about the magnetic field. Can we now get in experimental these fields, for example?
In experiment?
Yes.
But in the terrestrial condition, you mean, yes?
Yeah, no, I mean it's theoretical evaluation. Yes, you can calculate this. Can we receive this magnetic field in next experiment, for example, in the world? I don't know.
In the world?
No, in some experiment, I don't know.
But in the
you just figure field value field, magnetic field. Yes? Can we get this magnetic field, for example? Yes, receive.
We receive such magnetic field.
In which experiment, for example?
If I understood your question correctly, and you asked that, can we
image some
or not? Yes.
Yes. It's available now.
Okay, yes, I say that. In the terrestrial condition, by Bohmic method or impulsive method, only 10 in power 7 or 8 is produced.
So.
But in heavy ion, non-central heavy ion collisions, and when the chiral magnetic field effect is observed, it is not excluded 10 in power 20 Gauss is produced when the quarks are directed along one line. Okay, it is not excluded. It is indicated by Farzeyev, McLaren, and Kiblikov or other people. Okay, yes. But in the cosmos, for example, there is paper written by Witten. Okay, there should exist the field higher 10 in power 20 Gauss. For example, in the around the cosmic superstrings, there should exist 10 in power 46, 47 Gauss. It's possible. In magnetars, it is there should exist 10 in power 15 Gauss. 15 Gauss. But normally, when electroweak symmetry breaking is restored, it is required 10 in power 24 Gauss. But our limit is less than 24 Gauss, between 22 24 Gauss. Okay. Why we take this one on the other hand? Because when it's Schwinger, for example, Schwinger field intensity, in that case, muons cannot be produced in the low lambda level. They should be produced on the higher lambda level, but it is not the case here. Okay. Therefore, we take such high magnetic fields, and it is derived from the estimation, normal physical estimation.
Thank you very much.
Thank you.
Any question from online?
Thank you.
Thank you. Next. Thank you very much, Dr. Hussein.